Hello, my name is David, and I'm so excited to be your computer science teacher. Today's topic is data representation. Data representation is one of the major topics in AP Computer Science Principles. So binary code, which I'm sure many of you have heard of, is one of the major components of data representation. Binary code consists of ones and zeros, as you can see on the screen here. So before we go on, I just have one question for you. Are computers smart? Well, computers are smart in many of the ways that humans are not. They can perform calculations this quickly. They can store massive amounts of information for a long time, accurately as well. But computers are not smart in the ways that humans are. Computers tend to be very literal, and computers don't know anything you don't tell them. To give you an example, let's look at this. How's the weather in this picture? Nice and sunny, isn't it? So imagine it's Friday night. Your dad says to you, tomorrow, if it is sunny, we will go to the beach. Well, tomorrow rolls around and guess what? How's the weather? It's rainy. Question, do we go to the beach? You're probably thinking no, because you understood implicitly that your father meant if sunny, go beach. If no sunny, no go beach. But from the perspective of the computer would say to you, beep beep boop bop, you only told me what to do if it's sunny. You didn't tell me what to do if it's rainy, beep beep boop bop. So keep that in mind for how computers think. So now let's go into binary. First, what is binary? I'll give you some words that begin with BI. Bicycle, biannual, bilingual. Hmm. Bilingual means how many languages? That's right, two languages. Biannual means every how many years? That's right, every 2 years. And bicycle, for a bicycle, how many tires are there or how many wheels are there? That's right, there are two of them. So fundamentally, at their core, computers only know how to do two things. You can think of them as on or off, yes or no, or in terms of binary, one or zero. Okay, so quick question. Which one means yes, one or zero? That's right, one means yes. Which one means off, one or zero? That's right, zero means off. But I'm currently using a MacBook Air. I can listen to music on it, I can write documents on it, I can watch videos on it. Your computer can do much more than just turn itself on and off, right? So your computer uses those two things to do everything it knows how to do. So what do you see here? It's a Microsoft Word document. I'm sure that many of you have done things with Microsoft Word before, written an essay for school, etc. Well, guess what? Ultimately, behind each Microsoft Word document is probably thousands and thousands of ones and zeros. What's this? YouTube? Just like you, I myself watch a lot of YouTube videos. I do it for entertainment, I do it for education, or even just to listen to music to pass time. Behind each YouTube video, ultimately, is a bunch of ones and zeros. For high quality or high definition YouTube videos, it's generally in the billions. You'll have billions and billions of ones and zeros. So now, before we do binary, let's just talk about regular numbers that humans use. What number is this? That's right, 3,294. There's no reason I chose this. It's just a randomly chosen number. If you notice though, 3,294 actually could be written this way. 3 times 1,000 plus 2 times 100 plus 9 times 10 plus 4 times 1. What do you notice they all have in common here? What do these all have in common? They are all base 10. What does that mean? Well, if you look here, 1,000 is the same as 10 to the third power, so with a base of 10. 100 is the same as 10 squared. 10 is the same as 10 to the first power, and 1 is the same as 10 to the 0 power. So during my classes on Outschool, I would have students give me some three-digit numbers at this point. But since this is a YouTube video, I'll just give one to myself. Let's try 284. 284. Well, 284 could be further written like this. 200 plus 80 plus 4, which, which can also be written like this. 2 times 100 plus 8 times 10 plus 4 times 1. Finally, they can be written like this. 2 times 10 squared plus 8 times 10 to the first power plus 4 times 10 to the 0 power. Okay? So now it's your turn. Either on your device, your tablet, or on a piece of paper. Break these down the way I just broke down the previous numbers. Feel free to pause the video right now to do so. Okay, well done. Well, this is called the decimal system, also known as the denary system. Deci means 10, hence base 10. The word denary is primarily used, I believe, in the UK or places that use the British curriculum. But either way, decimal or denary, they're the same thing. I will accept both interchangeably. So the decimal system is also known as the base 10 system. So just some fun history. It was invented in India, moved over to the Middle East, and then brought to Europe. So what are some advantages of it? Well, it's quite simple for humans. I mean, we have 10 fingers, right? So 10 is easy for us to understand and conceptualize. But actually, it doesn't exist in nature. Animals don't have any special concept of 10. This is just a form of representation that humans made up. We could just as easily make up a different representation system. How about this? You see some tally marks? Yeah. Does this make sense? Yeah, of course it does. So this makes good intuitive sense, but can you imagine doing 1 million plus 1 million using tally marks? I don't think so. That'll take a long time. You'll probably make some mistakes as well. What about this? You see here, these are Roman numerals. So symbolically, they are a step up from here. But I personally prefer our current numbering system. So again, these are all just forms of representation. And speaking of representation, that's exactly what binary is as well. So in binary, 000 in binary is 0 in decimal. Hmm, okay, looks pretty similar. 001 is just 1 in decimal. Well, binary looks a lot like decimal, doesn't it? Well, here's where things start to get fun. 010 is equal to 2. 011 is equal to 3. What do you think 4 is then? 100. What do you think 5 is? 101. In a previous class I taught, a student saw this and then asked me, do we have to memorize this? The answer is no, you don't have to memorize it. I mean, you probably will just because we're going to do it so much, but you do not have to memorize it. And you'll see why. So each of those numbers, each one and each zero, is known as a bit. Bit is short for binary digit. Have you seen this before? It's a Bitcoin. Now you know where it gets it. Now you know where the Bitcoin gets its name from, because behind each of these is a bunch of ones and zeros. Right. So you're probably wondering how binary works then. How do we go from a bunch of ones and zeros to other numbers? Well, here's how it works. This first bit is in reference to 2 to the 0 power. This second bit is in reference to 2 to the first power. This third bit is in reference to 2 to the second power, and so forth. Remember what I said about ones being yes and zeros being no? Right? So keep that in mind. First, what is 2 to the 0 power? That's right, it's 1. What's 2 to the first power? 2. 2 to the second power? 4. 2 to the third power is 8, and so forth. 16, 32, 64, and 128. Notice each of these is just double the previous one. So now let's do some more math. Take this number, 0 times this number, 1, plus this one here, 1 times 2, plus this one here is 0 times 4, plus 1 times 8, plus 0 times 16, plus 0 times 32, plus 1 times 64, plus 1 times 128. Because anything times 0 is 0. You see here, anything times 0, we'll just ignore that and only write these ones. So 128 plus 64 plus 8 plus 2 gives you what? Go ahead, take your calculator out. Feel free to do this with a calculator. You can pause the video if you'd like. The answer is 202. So it's 202. Now let's do some together. 0, 0, 1, 0, 1, 1, 0, 1. Well, remember, 1 means yes, 0 means no. So 1 is yes for 2 to the 0 power. 0 is no for 2 to the first power. Yes for 2 to the second power. Yes for 2 to the third power, and so forth. So this ends up being 1 plus 1 plus 4 plus 8 plus 32, which gives you 45. How about this one? This one is 0 plus 2 plus 4 plus 0 plus 16 plus 0 plus 64 plus 0, which ends up being 86. Now, how about this one? This is 1 plus 2 plus 0 plus 0 plus 0 plus 0 plus 64, which ends up being 67. All right. Okay, so it's your turn. Do these on your own. Feel free to pause the video. All right, so the first one is 55. Second one is 69. Third one is 100. All right, so great job. Hopefully you got them all right. Are you wondering why only ones and zeros? Well, it's because computers are powered by what? Electricity. So either electricity flows or it doesn't flow. You cannot partly let electricity flow. Maybe in some sort of quantum computing, but we're not going to get into that for AP Computer Science principles. So you have many, many switches inside of your phone or computer known as transistors. What is a transistor? It is a semiconductor that switches electrical currents on or off. You probably have millions or billions of them in your laptop, your TV, or your phone. Question: is there a way you could tell just by looking, without calculating, whether a binary number is odd or even? In fact, there is. You look at the last number. Remember, the last number means 2 to the 0 power. What's 2 to the 0? 2 to the 0 is 1. So that's the only odd number we're talking about here. If that's a 1, it's odd. If it's a 0, it's even. So this number here is even. This number here is odd. This number here is odd. Okay? So we've been talking a lot about bits. Binary digit meaning bit. Well, bits are very small pieces of information. We often speak more in terms of bytes. So 8 bits forms 1 byte. Another fun fact, 4 bits is actually called a nibble. Pretty funny, huh? I guess computer scientists have a sense of humor. So you've probably heard of the terms like 8-bit or 16-bit or 32-bit or 64-bit. Most computers today are around 64-bit. Computers from the 90s, I believe, were mostly 32-bit. But almost all electronic devices will be at the very least 8-bit. So even a byte, which is 8 bits, is a very small unit of measurement. You've probably heard of the term kilobyte before. So kilo means what? Kilo means 1,000. What comes after that? Mega. Megabyte, and then, so mega means a million. Giga. means billion. And then what's after that? Tera. Tera means billion. Oh, no, sorry. Tera means trillion. But mathematically, so yes, a kilo means 1,000, mega means a million, giga means a billion, and then tera means a trillion. But mathematically, can you find me a number? Can you find me x such that 2 to the x is equal exactly to 1,000? Go ahead, I'll wait. Feel free to use your calculator. So if you try using a calculator, you'll find that there is no integer. There's no integer value of x that gives you exactly 1,000 when you raise 2 to its power. It's like 9 point something that gives you 1,000. So actually, kilo means 2 to the 10th power, which is 1,024 bytes. Mega usually means a million, but in this case, it's 2 to the 20th power, which is 1,048,576 bytes. You see the same pattern with giga and with tera. So these terms don't match exactly with the number of bytes simply due to mathematics. Question: what is the highest decimal number that can be stored in 1 byte? So again, how many bits are in 1 byte? 1, 2, 3, 4, 5, 6, 7, 8. So the highest is, of course, when everything is turned on. 1, 1, 1, 1, 1, 1, 1, 1. Okay? So why don't you go ahead? Feel free to use your calculator. What is this? It ends up being 255. Interesting, interesting. But wait a minute. Wait a minute. Isn't 2 to the 8th power 256? What accounts for the difference of 1 here between 256 and 255? Because of the existence of the number 0. So the first number is actually 0. That's when 1 byte is 0, 0, so 0, 0, 0, 0, 0, 0, 0, 0. The second number is 1. The third number is 2. Right, so what does it mean for a computer to be 16-bit? 8-bit only goes up to 255 different possibilities. 16-bit is much more. It is 65,535 different possibilities, right? So you're probably thinking to yourself, I don't remember the last time I texted my friend saying like, hey friend, 10001, 11001, 1000111, I don't think you text your friends message, you just text your friends saying like that, right? You probably text your friends something more plain, like this, like, hey Sarah, are you going to the movie night on Saturday? Totally, I was hoping you'd come. It'll be fun. So how do we get from 255 different numbers to represent things like letters and punctuation marks? This is known as encoding, in which you turn things into code. So we'll just have to agree that maybe the decimal number 1 is equal to capital A, the decimal number 2 is equal to capital B, 3 is equal to C, and so forth all the way up to Z, which is 26. I know I said decimal, and it says denary here, but remember, they're the same thing. So, how would you write the word hello in all caps? Well, it would be equal to 8, 5, 12, 12, 15. Of course, for the computer, lowercase e and uppercase e, they're different. So you'd have to account for lowercase letters too. Maybe 27 is then lowercase a. So lowercase a. Turns out this is pretty much exactly how it works, just with different numbers. In 1963, what's this? ASCII. It's pronounced ASCII. ASCII was first published. So please memorize this. ASCII stands for American Standard Code for Information Interchange. So here's what the original ASCII table looks like. And here's what the ASCII table looks like right now. You do not have to memorize it. In my class, you're allowed to print it out and bring it with you on tests. Notice here, there's also hex. Hex means hexadecimal. Don't worry about that for right now. We'll cover that in a future lesson. Pay attention right now to decimal. So if you look here, 65, the decimal number 65 is equal to capital A. 66 is capital B, and so forth. So then what was capital HELLO in all caps? HELLO. And voila, looks like all caps hello is equal to 72, 69, 76, 76, 79. So imagine your friend sends you a text message like this in binary. Now, before you block and unfriend that person, let's translate the message. How do you do this? Well, all you have to do here is what we did earlier. Remember, this means to the zero power? No. To the first power? No. To the first power, to the second power? No. To the third power? Yes, we'll keep that one. To the fourth? No. To the fifth? No. To the sixth? Yes. To the seventh? No. So what does that end up being? 64 plus what? Plus 8, which ends up being 72. So why don't you go ahead and pause this video and do it for the other three. 72, 101, 121, and 33. Hey, we're not done yet. Now, look back at the ASCII table. What does 72 correspond to? What does 101 correspond to? What does 121 correspond to? And what does 33 correspond to? It ends up being capital HEY exclamation mark. Hey! So again, your turn. This one's quite long. So usually what I do in class is I split learners up. One person does the first two, another person does the second two, someone else does here, and someone else does here, and someone else does the rest. Mhm. Since this is a video on YouTube, you should feel free to go ahead and pause right now, calculate all of these. All right, so it looks like you've done that. This is what it ends up being. The message is capital R space U space HUNGRY question mark. So thank you everyone for watching this video all the way through. I hope that was helpful. If you're interested in learning more computer science, I offer classes on Outschool. I also offer personal one-on-one tutoring, and I plan to release some books on Amazon Kindle Direct Publishing soon, so keep your eyes peeled for that. I also plan to sell this PPT on Teachers Pay Teachers, so I will let you know when that's available. Hopefully you found this helpful. Stay tuned for more lessons to prepare yourself for AP Computer Science Principles, for the AP exam, for the class, or just for fun. Thank you very much. See you again in the next video. Bye.